So today the big is we're going to start with polar coordinates, and I'm going to tell you what it actually means. I'm not going to assume anything because the tendency is we all know something, and some of us know a lot, but probably nobody knows everything they need to about it. And there may be some misinformation or just, the wrong connotation of what something means. So here's how it works. I know what XY plane is. We'll get to that in a bit. But polar coordinates, basically, you start with a point, and that point is called the pole. The point, if I'm relating it to the XY plane, it's the starting point. So in the XY plane, what would you say is the quote unquote starting point of all measurements in the XY plane?
The origin.
The origin. So the pole basically is the equivalent of the origin. Then we draw a ray from the pole, and the ray points in the direction of the positive x-axis. And that's actually quite important. This has to be horizontal. Therefore, now every point, and this is only two-dimensional, every point that I can possibly come up with, I can then draw a line segment from the point to the pole, and there's two things I can measure. I can measure this distance, which we usually will call r, and I can measure this angle, which we'll generally call theta. That means that every point on the XY plane, right, there's no XY yet, but every point on the plane is measured as the distance from the pole and the angle made if I drew a line segment with the pole. But that also means that if I added 2 pi, and usually we usually use radians for this out of convenience. So if I added 2 pi to the angle, I'd still be at the same place. Oh, so if I add any multiple of 2 pi to this angle, I'd still be at the same place, which right off the bat means there are an infinite number of representations if I use polar coordinates. So polar coordinates have only to do with the r and the theta. So now how do we relate that to the XY plane? And by the way, I find it amazing at this level. I teach the smartest people that I know, and most students tell me they did not know that's where the word polar coordinates comes from the word pole, and the word pole, that is the origin. It's actually that simple. There's nothing tricky, nothing hidden. So now let's look at an XY plane. And so in the XY plane, if I have a point, now let's call that point x comma y. I can still measure this distance here, and I can still measure that angle there. But now what we want to do is relate r theta to x and y. So the first thing we always do, let's make a right triangle. So that would mean that that length right there is x, that length right there is y. So right off the bat, do you all agree that x squared plus y squared is equal to r squared? That's kind of the first oh duh. Now let's go very SOHCAHTOA-ish, okay? What is the cosine of theta? Anybody? What is the cosine of theta?
Y over r.
The other guy.
X over r.
X over. Cal. So this would be x over r, and that simply means then that x is r times the cosine of theta. All right, what's the sine of theta? Now, Joshua, what's the sine of theta?
It's y over r.
Y over r. Which means that y equals r sine of theta. So that's one, that's one, that's one. There is one more, but it's really not that critical, and that is that the tangent of theta must be y over x. But we have to be careful because using inverse tan to find something isn't really useful. Remember, inverse tan only returns values in the first and fourth. So if I'm in the second quadrant, I'm going to get the wrong answer. This is one, but this isn't the one we generally use. We generally use these. Okay. And when I mean use them, I mean to move back and forth seamlessly from the rectangular coordinate system to the polar and so on. So with these identities, then I can take any point on the XY plane and translate it into polar coordinates. But like any substitution, the substitution is done all at once. Okay, a lot of times we have difficulty when we're doing integrations that involve substitutions. Some people will do a u substitution, but we'll still have u and x at the same time. Mathematically speaking, a substitution, every substitution that exists is done at one time. It's not done piecemeal. So if I'm doing polar, I'm swapping out X and Y for R and theta. I cannot have X and R in the same statement at the same time mathematically. That doesn't have any meaning. I do it all at one time. And so one of the first things we want to be able to do is translate. So if I gave you an equation in R and theta, can you translate it to X and Y? If I gave you an equation in X and Y, could you translate it to R and theta? It's actually that simple. So one of the problems that you run into a lot in Calc 3, a very common problem in Calc 3 will be an integration involving something of the form, let's say x squared plus y squared to a power. And the power is usually going to be either an integer exponent or something with halves, like the 1/2 power, 3/2. Think like binomial formula. But we're not going to do a summation. We're not going to do a binomial expansion. So what we would do is we'd say, this problem will be much easier if I change it to polar coordinates. And what we do is we make that into then r squared to the k power. Okay, this is maybe the single most common move in all of Calc 3 integration that exists. This is probably the most common step you perform, is you see x squared plus y squared raised to a power and you swap it out for polar. And you take something that would be extremely difficult in the XY world and you make it something really easy in polar world. So this is an example of the kind of thing you would do. So in general, if I've got x's and y's and I want to convert to polar, then all of the x's are replaced with r cos theta, all the y's are replaced with r sine theta. But you notice I didn't do that here because I already know that sum is r squared. So what if I had something of this form, let's say? Now I can't do the r thing. This is not square root of r. No. This would now be r cos theta plus r sine theta. And then I would raise that to a power. So that may be the direction I'd go now. Okay. So this is a simple example of a very easy substitution. So let's do an example of something we might see. Now, I want to remind you of something, mathematically speaking, and this goes back to baby algebra. You're solving an equation, and in remedial algebra, you might have had a problem of this nature. I don't even care what the answer is, but you might have had a problem of this nature. Maybe, I don't know, let's say 2x over x squared minus 4 plus 1 over x minus 2 equals 2 over x plus 2. You had something like this. And this problem right here can be really, really difficult. Right? I got too much going on here. This is a problem from Math 46. This is a problem from elementary algebra. Well, the only way I can solve this problem, the only way, is to multiply through by a common denominator, because right now there's too much going on. I have 3 different denominators. So what we would do in remedial algebra is that we would multiply both sides by x squared minus 4, because that's x plus 2x minus 2. Now, when I do this, I will have a very, very simple linear equation. Easy peasy. And I get an answer all the way at the end of the problem. But here's the thing. Right now, I just wrote a problem. If I change the coefficients, every time, leave the numerators intact. Every time I change any of these numbers, it would completely change the answer, which means technically something of this form would still have an infinite number of possible solutions. If I make that 1 into a 3, if I make that into a -1, if I make that into a 4x, every time I make one change, I will get a different answer. Therefore, every possible real number is truly fair game. So what if I did this problem all the way to the end, and at the end of the problem I got, and then x equals 2. And I did everything right. And by the way, it'd be really easy for me to make this so that is the answer. That's not really very hard to do. What would that mean if that's my final answer? You notice anything kind of wacky about x equal 2 as a final answer?
It's not defined.
Yeah, it's not even in the domain of possible answers yet. It would be very easy for me to, all I got to do is change one number and I can make it so that that's the answer you get. That answer is impossible. So we would say, let's say that's the only answer I got, then this actually truly would have no real solution. What if I got 2 answers? What if I got x equals 2 and x equals 4? Then you'd say this one is extraneous because, again, it's not a possible answer. But the only way I could get an answer was to multiply both sides by the common denominator. But when you remember, there's only a couple really simple rules that you can't violate. You can never multiply or divide by something that can potentially equal what? Anybody? This is a never, as an absolute. You can never multiply or divide by something that can potentially equal
0.
0. Oh, remedial algebra. Remedial algebra. Solve x squared equals x. What do remedial algebra students do? I divide both sides by x and I get x equal 1. Life is good, except that's not the answer. But 1 squared equals 1 is true, but that's not the answer because you performed the ultimate illegal step. See, the only way this can be done is to do this. Why is this the wrong answer? Because that's the right answer. There are 2 solutions to this. What happened to the 0? I divided both sides by a quantity that could potentially equal 0, and therefore I removed 0 as being a possible answer. That's why it's an illegal step. If I multiply both sides by something that can potentially equal 0, then I may introduce something as a solution that should not be there. Now, I'm pointing this out because this is exactly what we're going to have to do to solve some problems. We're going to have to multiply. We're going to have to do some algebra that may be edgy. So in remedial algebra, let me remind you of something. I mean, you guys know this. You probably haven't done it a lot recently, but in Calc 1, we do it all the time. Baby algebra. I've got something of this one. We'll keep it really simple. Let's say I have, I want this to be easy. Let's say x minus 2 over x squared minus 4. Right now, what is the domain of this in words? What is the domain? Not intervals, just words. You'd say all reals.
Except for x equals 2 and negative 2?
You'd say all reals except for x equals 2 and negative 2. And I prefer an answer in words rather. Intervals are fine, but in words, everything but 2 and negative 2. But obviously, if I'm doing this algebraically, I can cancel something, right? So I know algebraically this is equal to this, or is it? Because if you walked in the room right now and looked at this, wouldn't you say the domain of this is all reals except for negative 2? But you said this was all reals except for 2 or negative 2. That's a problem. Can 2 be in the domain of this answer? Can I insert a 2 into there? Well, if I can't hear and these are equal, can I hear? No. X equal 2 is what we call a removable discontinuity. Hopefully that rings a bell because I basically just removed it from the problem. But this in remedial algebra, this is what we do. I throw in a disclaimer. This is identically equal to this as long as x is not equal to 2. But isn't this exactly how we do limits? You see, don't we do this? The limit as x approaches 2 of x minus 2 over x squared minus 4. Well, right now, this is the indeterminate form 0 over 0. Numerator and denominator both tend to 0, so I cannot evaluate it. 0 over 0 isn't a number, it's a behavior. But I can say that this equals this because I factored and canceled. Now remember, this means x approaches never reaches. So 2 is not in the domain. I'm never going to evaluate this at 2 because 2 isn't even in the domain. Oh, but the limit says as x gets closer and closer to 2 here, it's the same as x gets closer and closer to 2 here. And as x gets closer and closer to 2, this quantity is getting closer and closer to 1/4. So the limit is 1/4. That's equivalent to saying the ordered pair 2, 1/4 on this graph has been removed, but there's only one point missing, and the limit is where I would have gone if the point were there. Now, this is Calc 1, we know this, but what allowed us to do this problem was this thought of a disclaimer here. These are identically equal as long as x is not 2, because I factored and canceled. Now, the flip side is, what if I multiply? Because that's both factoring and canceling and multiplying to make my life easier are optional steps, but we have to know, am I changing the very nature of the problem if I do an algebraic step? So let me start with something easy. I do this in the classroom every time. All right, I'm going to start with a mathematical statement. X equals 2. That's it. Okay, there's a classic Far Side. That's a comic. There's a classic Far Side, one of my all-time favorites. Teacher's in front of the room. There's a gigantic picture of a cow, and under it, it says cow. And the teacher's asking, any questions? And every hand is up, and it just says, it's like class of fools or something to that effect. It's a picture of a cow with the word cow and any questions, and everybody has a question. X equals 2. Are there any questions? Well, there really shouldn't be. X is 2. That's not very exciting. I'm just making a statement. Now I want to manipulate that. The addition property of equality says if you add the same value to both sides of an equation, you preserve the equation. That's how we solve simple linear problems. The multiplication property of equality says if you multiply both sides of an equation by the same non-zero value, you preserve the solution. That's how we solve a lot of problems, getting rid of coefficients, things like that. So just for the heck of it, let's multiply both sides by X. All right, I want to multiply both sides of this by X. And it doesn't matter which side I multiply because multiplication is commutative. Okay, great. So now I've got X squared equals 2X. And that's X squared minus 2X equals 0. That's X times X minus 2 equals 0. So X equals 0 or X equals 2. Okay, that's really exciting. I know you're calculus folks. Is this at least a little bit interesting to anybody? This last line? Anybody find the last line at least intriguing in a small way?
You multiplied by a potential 0 number.
Let's put it this way. How did I grow a 0? Didn't I start by saying X is 2, period? How did X equal 2 become X equals 0 or 2? Well, it's because I performed an extremely illegal step. I made a gross mathematical error. That doesn't mean ooh, disgusting. That means astronomically large. And you're going, where? Well, let's work backwards. This clearly came from here, and that clearly came from here, and that clearly came from here, and that clearly. So what's the illegal step, Joshua?
I guess when you multiply by X, X could be.
And I multiplied both sides by X. That was the illegal step. I just multiplied both sides of the equation by a quantity that could potentially equal 0. And what did I get as an extraneous solution? 0. Let me put it another way. Let's suppose I multiplied both sides by X minus 10. We would have seen X equal 10 as a solution. Oh, so that step was illegal. The problem is I sometimes have to do a step of that nature in order to solve a problem. And what I mean is, I did an example earlier where I was clearing out denominators. There's no way around it. You have to do that step. So as long as you have the disclaimer, you see, this step is legal as long as I do what? As long as I throw in that disclaimer that I'm not multiplying by 0. And then when I got to here, you go, no. Extraneous. So here's what we're going to do. We're going to do stuff that requires polar conversions. All right, let's start with a really simple one. Let's do R equals 4 times the cosine of theta. This is an equation, and I would like to convert this into X and Y. I don't really have a conversion into X and Y. I mean, cosine of theta, I know that X is R cos theta, Y is R sine theta, and X squared plus Y squared is R squared, but I don't seem to have any of those right now. Anybody got an idea of a good first step? There's only one. I really don't like R, by the way. I really love R squared, though.
That one, square both sides. Or multiply both sides by R.
Yeah, I could try squaring both sides, but then the right side would involve a cosine squared, which isn't really any better. But how about multiplying both sides by R? If I multiply both sides by R, let me put it right there. Oh, R cos R squared. Now, did I just completely change the nature of this statement? Did I just introduce stuff that isn't there? Have I made an entirely new problem? Only if R equals 0 was not already possible. Here's what I mean. In the statement, R equals 4 cosine of theta. Are there values of theta where R would equal 0?
Yeah, definitely.
In the statement R equals 4 cos theta, what if theta was pi over 2? Start with a simple one. Wouldn't R equals 0 therefore be a solution? Everybody cool with that? Since R equals 0 already is possible in my original statement, then multiplying both sides by R does not introduce anything extraneous. That's extremely important. That's what makes the next thing legal. You say, well, wouldn't that always be the case? Arbitrarily, let me take something completely different. R equals 4 times the cosine of theta plus 1,000. Well, if I multiply both sides by R now, I have completely changed it. It's an entirely new unrelated equation because this R can never be 0. That plus 1,000 kind of prevented it. Since this R can never be 0, if I multiply both sides by R, it's a different problem. That's not a legal step anymore. And any conclusion I make really isn't important. But the nice thing about polar, more often than not, this step works. So now I have R squared equals 4R cos theta. Now it'll be really easy for me to substitute in terms of X and Y. So if I do that, the left side is X squared plus Y squared. What's the right side? Anybody? What's the right side?
4x.
4x. All right. X squared plus Y squared equals 4x. What is that? How about if I do this? I left a little space there. What's that little space for? Let's complete the square. So this would be X minus 2. So I need a plus 4 plus 4. Oh, anybody? What is this? Anybody, what is this shape? Exactly.
This is a circle.
Okay, there's only 2 things I need for a circle: the center and the radius. What's the center?
2, 0.
2, 0. And what's the radius?
2.
2. So this is a center. This is a circle. Let me erase this. Fit it in. It's centered at 2, 0. That means its center is on the x-axis. But if it's of radius 2, that's this circle right here. Now, never saw that in the original equation. Question is, could I have gotten that same picture by just plotting points? This is superior because I know R equal 4 cosine of theta is a circle of radius 2 centered at 2, 0. And notice my circle passes through the origin. The origin is R equals 0. Remember, you're always starting from the pole. So if your R is 0, then you never left the pole. So R equals 0 always puts you at the origin no matter what. So that's what that is. Could I have figured that out a different way? Yeah, I'm going to show you. What if I actually make a table of values? Now, let me go back to here. R equals 4 cos theta. Do I introduce the R and figure out the theta, or do I introduce the theta and figure out the R? I mean, what do you think? In other words, which one should I treat as my independent variable, R or theta?
I would change theta so that you can just figure out cos theta and get R from there.
Yeah, so in other words, we're going to treat theta as the independent. In fact, that's pretty much always the way it's going to work. We're always going to think of R as a function of theta, not the other way around. So if I came up with thetas, well, what sort of thetas should I use? I should probably use thetas that are easy for me to calculate. So maybe, for example, how about if I use something like, I don't know, 0, pi over 3, pi over 2, 2 pi over 3, pi. Let's just start with that. Why pi over 3? Because the cosine of pi over 3 is a half. Pi over 3 is a good one. I don't like pi over 6 or pi over 4 as much because that has square roots in it. Not that those are wrong, but this is easier. So when theta is 0, r is cos 0 is 1, so that would be 4. When theta is pi over 3, cosine of pi over 3 is a half, so r would be 2. When theta is pi over 2, cosine of pi over 2 is 0, so r would be 0. 2 pi over 3, cosine of 2 pi over 3 is negative a half, so r would be negative 2, which right away presents kind of a, I think the appropriate word would be a conundrum. And then at pi, I'd be negative 1, so negative 4. Let's go that far. And let's see what we get. Now remember, the angle is always made with the positive x-axis. So if I'm at an angle of 0, it means I went out 4 units. That puts me right there. So if I go out for about 60 degrees, is probably about, okay, this is not a great picture. That's probably too much. Maybe about, I don't know, about there. Okay. That's pi over 3. That's about 60 degrees. See that 2? I'm saying that length right there is exactly the same length as that. I just went out 2 units. Now, let's go an angle of pi. Well, then I'm 0 units. That puts me right here. Now, let's go at an angle of 2 pi over 3, which would be about there. I want to go in this direction, negative r units, which would just mean I'm going to go in this direction. And that would put me about right here. Now, pi. I want to go negative 4 units. That puts me back to here. Do you realize we just completed our entire circle going from 0 to pi? I don't need to go from 0 to 2 pi. There's a common misconception. Don't you always have to go 0 to 2 pi? Yes, when your shape is centered at the origin, you do. We're not centered at the origin. We just completed this whole circle from 0 to pi. Now, had I used pi over 4 and pi over 6, we would have gotten some other pieces. I just used the gimmies because I know that's the same length. That's 2, that's 2, that's 4. Doing it what we did before in equation form, vastly superior. But the point is, when I have something in polar coordinates, you always think of theta as the independent variable and r as a function of theta. That makes a huge difference. So I want to do a couple of simple graphs of polar stuff. Let's suppose, all right, let me start with a simple one. I'm trying to find a good black pen here. That's good. All right, so here's my equation. We're going to say r equals 4 minus 4 times the sine of theta. Okay. Now, you might say to yourself, you know what? I want to put this in rectangular coordinates. That is absolutely correct. There's never a time when it is incorrect, but it might not be efficient. It might not make my life easier. Now, in the last example, clearly it made it way easier. So is there a value of theta that would cause this quantity to equal 0? Sure. If theta is pi over 2, I'd have 4 minus 4 is 0. And I asked that question because I want to multiply both sides by r, totally legal right now. So when I multiply both sides by r, I get r squared equals 4r minus 4r sine theta. Perfect. That gives me now x squared plus y squared. Well, if r is x squared plus y squared, then 4r really has to be the square root of x squared plus y squared minus 4y. Beautiful. So I took this relatively simple r theta statement, and now I've made it into rectangular coordinates. Are you excited to work with this? First of all, you can't solve for y. Secondly, that's not a function. I took this and I made it into this. These are the same thing. I'll give you a month, but then you got to quit. I'll give you a month to figure out what that looks like. Derivatives, everything. Ain't going to happen. In fact, you're going, what points can I? Well, okay, I got one, 0, 0. If x and y are both 0, good, I got a point. And I'm not sure I can find another one. Yeah, I'm thinking this is not very useful. It's legal, but it's not useful. So I think we're better off leaving it in this form here. All right. So what we'll do is we'll just leave it like this and let's plot some points. I'll make it a long table. So theta, R. Now, because it's the sine function, I really don't want roots if I can have them. I'd really rather rational numbers. So let's, sine of pi over 6 is a half. So pi over 6 is a good one. So let's go 0, pi over 6, pi over 2, 5 pi over 6, pi. 7 pi over 6, 3 pi over 2, 11 pi over 6, 2 pi. Now, obviously, there's an infinite number of angles, but those are the only angles where I will actually get rational numbers, because I really don't want to labor. All right. So if sine of 0 is 0, so this would be 4. Sine of pi over 6 is a half, so now I have 4 minus 4 times a half, that'd be 2. Sine of pi over 2 is 1, so we're 4 minus 4, or 0. 5 pi over 6, the sine of 5 pi over 6 is a half, so now we're back to 2. The sine of pi is 0, so we're back to 4. With me so far? 7 pi over 6, the sine of that is negative a half. Ooh, that puts us up to 6. Sine of 3 pi over 2, that's negative 1. That puts us up to 8. Okay, 11 pi over 6, sine would be negative a half. That puts us back to 6. 2 pi, the sine of that is 0. So you can see my judicious choice here. Now I'm going to do something that you may or may not be familiar with. I'm going to create what's called polar paper. Now you may have done this in a trig class, pre-calculus class, or maybe even in a physics class. A polar paper would be concentric circles. I'll do my best here. Yeah, let's pretend that these are good. I know they're not great, but good enough. Okay, this is polar paper. And the second thing you do with polar paper is that you, oops, just that one better. I can do circles, I can't really do line segments. Probably should have gone through the middle there. Try that again. Okay. Now what you do is you'll see all sorts of lines, and all of those lines refer to angles. So right now that would be the angle pi over 2. So if I wanted, let's say, the angle of pi over 6, I would do that one. I want the angle of 5 pi over 6. So if I do that one. Now, I can keep going all the way around with these lines. I don't need to, because I'm just going to use the ones I did. But the beauty of polar paper is that you just go out that many units on the graph. So at an angle of 0, I'm going to go out 4 units. And let's suppose my rings are every 2 units. So that's 2, 4, 6, 8. Otherwise, I got to draw a lot more circles. Angle of 0, I'm going to go out 4 units. So that's 2, 4. So I'm right there. At an angle of pi over 6, I'm going to go out 2 units. So that puts me right there. At an angle of pi over 2, I'm going to be 0 units. That puts me at the origin. Okay, that's kind of interesting, isn't it? 5 pi over 6, I'm going to go out 2 units. So that puts me here. And at pi, I'm going to go out 4 units. So that puts me here. Wow, hard to tell what's going on so far. 7 pi over 6, I'm going to go out 6 units. That puts me here. 3 pi over 2, I'm going to go 8 units. That puts me here. 11 pi over 6, I'm at 6 units. That puts me here. And at 2 pi, I'm back to here. So what is this thing? It's hard to tell because I got all those lines. Can anybody tell me what does that look like? Think Valentine's Day.
A heart.
It's like a heart. What's the medical term for a heart? Anybody know? Like you want to do some heart pumping exercises. What do we call that? Riding your bike or something?
Cardio.
Cardio. Yeah, that means heart. This is called
Cardioid.
a cardioid. Exactly. The oid means like. It means heart-like. It's called a cardioid. And it's actually a really cool shape. This produced a cardioid. Cardioids will be produced with sines and cosines in varying degrees like this. Now, the cool thing about that cardioid, it's not that hard to draw, and I have a pretty good idea what it looks like. Now, I'm never going to ask you to use polar paper. I did this because it makes the physical graphing of this so much easier. This is a lot harder to do on the XY plane, but I want to actually do this on the XY plane at some point. So let me now translate this back to the XY plane. You're not going to be asked to draw things. No, but like in Calc 1, you have to know what it looks like. If you don't know what this looks like, you won't be able to do the calculus of this, which involves things like slopes of tangent lines, finding the area, looking at it in 3D. Yikes. So the shape that I just did, okay, basically you went down 8 units here. You were 4, let's try to get some perspective, about 4 units here. And it was something like this. Oh, sorry, that was awful. Let me try that again. That's kind of what you just, okay, I know it's not very good. I can do circles. That's kind of what we just drew. That's what that's telling me. But I'd like to know things like, where are the horizontal tangents? Where are the vertical tangents? Do you all agree that we probably have 1, 2, 3 horizontal tangents? And we probably have a couple of vertical, and certainly something really cool is happening about right there. So that's our next thing. How do I know about the tangent lines on a polar graph? Well, we need to define how to take a derivative, because next day what we're going to do is do integration. See, today I want to know where the horizontal and vertical tangent lines are. I want to know the slope at any angle today. Tomorrow I want the area of this thing. Okay, so what we already know from before that if x is a function, x is a function of t and y is a function of t, we showed before that dy dx, remember, was dy dt over dx dt. Okay, piece of cake. So we're going to do something really similar. Now we're going to say x, which is r cos theta, we're actually going to write as r of theta cos theta, because I said you're always going to think of theta as the independent variable, and r is always going to be a function of theta. The cardioid I just drew, I wrote r equals. The circle we drew, we did r equals. And then we had all theta on the other side. So this statement here, think of in this form. Y, which is r sine theta, think of as r of theta sine theta. So now I can employ this. Oh, right, way over here. So if I want dy dx, then what I want to do on top is what? Dy d theta over dx d theta. Before, our parameter was t. Now, technically, aren't I saying x is a function of theta when I write it in this form? I'm saying x and y are both ultimately functions of theta because r is a function of theta. So we want to do this. And this is not that hard. It just is going to involve product rule. So let's start with the y. Okay, first times derivative of second. And by the way, you don't need to write r of theta. You can just write it as r. So that'd be r cos theta plus the second times the derivative of the first, which would clearly be dr d theta. Okay, now x first times derivative of the second, so that'd be negative r sine theta plus the second times the derivative of the first. And it turns out this is the formula for finding the derivative of anything in polar form. It's actually, that's it. All I'm using is this formula here, which we derived last week. Okay, that's actually not that terrible. So let's do some simple ones. All right, let's start with, let's start with the circle that we did. Okay, because I think it's really easy to conceptualize that one. We did a circle a little while ago, r equals 4 cos theta. Okay, that's my r of theta, if you will. Now, we changed it to xy world, and then we wrote an equation in x and y, which was extremely useful for me to identify. Now I already know what a circle looks like. Anything where it's r equal cos or r equal sine is going to end up being a circle because of the whole multiply both sides by r, complete the square, all that stuff. I'd like to know what is the slope of the tangent line at every point on this. So let me just do a couple little things. First of all, what's dr d theta? Because that's going to show up twice. Dr d theta is clearly going to be -4 sine theta. So for this problem right here, the slope of the tangent line, oops, or you can just say m if you want, is r, oops, sorry, 4 cos theta. I'm actually putting that r right here. So 4 cos theta times the cosine of theta plus the sine of theta times -4 sine theta. Okay, that's my numerator. Over -r sine theta plus cos theta times there. This is the slope of the tangent line at every point on that. Well, in its current form, it's not very useful yet. We're going to make it useful. But right now, it's not entirely useful. So when I'm looking at that going, well, there's too much going on. If I gave you a particular theta, you could easily plug it in there. But why don't we see if we can simplify this mess, okay? You know, it might be a good idea if I just simply wrote the derivative formula down. No, I don't bother writing down. Let's just do it. So on top, what have I got? I've got, if I factor out the 4, yeah, I'll go ahead and factor out the 4. Then I have cos squared theta minus sine squared theta. On the bottom, I have -4 cos, -4 cos. So I have the same thing twice. So what if I factor out a -4 and I write it as 2 sine theta cos theta? Anybody see anything clever and useful here besides canceling the 4s? What's my numerator? Anybody? Cos squared minus sine squared? It's a really important identity there.
Is it the double angle formula?
It is exactly the double angle formula. It's the top is what? I'll leave the 4 in there for a second. That's cosine of 2 theta. How about 2 sine theta cos theta?
Sine 2 theta.
That's sine 2 theta. Ah, this is getting better all the time, isn't it? And so my answer is negative cotan 2 theta. I know you don't love negative cotan, but you know what? I'll take that over that any day of the week. Okay, that's a little bit easier to work with. So now let's go back to our picture and let's see if this makes any sense. I'm saying for this polar graph, the slope of the tangent line for every value of theta is simply this. Do it like this, make it easier on myself. Now, we agree that this should have a couple of vertical tangents, probably right about here and here. Okay, this corresponds to an angle of 0. Now remember, cotan is the reciprocal of tangent. Tangent of 0 is 0, cotangent of 0 is undefined. Okay, so at this place I'm undefined. Tangent of pi over 2 is undefined, but cotangent of pi over 2 is 0. When is my angle pi over 2? That means theta would have to be pi over 4, wouldn't it? Well, let's see, where's pi over 4? Well, that was 0, that was pi over 2, so pi over 4 is, if I drew this well, is about right there. Gee, what do you know? Look at that. That's not that bad. I have a horizontal tangent when my angle is pi over 4. Cool. I have a vertical tangent when my angle is 0. I'm also going to have a vertical tangent when my angle is pi over 2 because cotangent of pi is also undefined. How about down here now? Well, it turns out if I take my angle, okay, we said that was pi over 2, so now this is 3 pi over 4. And that will put me down here. So I have two horizontal tangents, I have two vertical tangents, and they're actually very easy to find. So it's extremely useful to be able to do a polar derivative. So in general, a polar derivative, all that means is I'm taking the derivative, but I'm leaving my answer in polar form, not XY form. If I put this back into the equation of a circle, I believe the equation was this. Do we all agree that that was the equation? If I asked you to tell me the slope of the tangent line, you could all do it, but what would you have to do? Not your favorite thing. I want dy dx. What am I going to have to do?
Some implicit differentiation.
I'd have to do implicit differentiation, which is absolutely correct. But if I do this implicitly, I can already see that's going to be a bit of a hassle. I'm going to get this in Polish. No, I'd rather do this. This was easier. Yeah, it's totally legal to do it implicitly, but it might get a little bit on the gnarly side. Okay, I'd really rather not do it that way. Now let's do the cardioid we just did. Let's see what the slopes of the tangent lines of that thing look like. Oops. My hands keep cramping up on me here. Hold on. Figure out which pen still has ink in it. So I believe our cardioid was r equals 4 minus 4 sine theta. So the first thing I'm going to do is find dr d theta, because that shows up in both numerator and denominator. Dr d theta in this case is just going to be negative 4 cos theta. That's easy enough. Okay. So now my dy dx, using the formula that we just derived, okay, write down. So dy dx is, now remember what it starts with? It starts with r cos. So it's this quantity is my r. Okay, and then plus sine times dr d theta, which is here. Okay, now on the bottom, I'm going to have the negative of r sine. So negative 4 minus 4 sine theta. Okay, then of course, plus the cosine times the derivative. You're going to see lots of sine squares and cos squareds. Plus cosine. Now, I don't know how this is going to reduce. I don't know if this is going to be convenient or not. So let me see. Blue pen here. Let's go ahead and distribute. I probably can lose some 4s, but not yet. So on top, I'm going to have 4 cos theta minus 4 sine theta cos theta minus 4 sine theta cos theta. That's a good thing. On the bottom, negative 4 sine theta plus 4 sine squared theta minus 4 cos squared theta. I think at this point, I'd just get rid of all the 4s. I think that will make it easier. So now I have on top cos theta, and those clearly can combine. So minus 2 sine theta cos theta. On the bottom, I'm going to have negative sine theta plus sine squared minus cos squared theta. All right. Now, you could certainly employ the double angle formulas. That would be absolutely correct. I can employ the double angle formulas. And then if I ask you to evaluate this at any particular value of theta, that'd be a piece of cake. But you know what? If I ask you to evaluate this at any particular value of theta now, you could still do that. That's really not that hard. But here's the caveat. What if I said, where is this equal to 0? For what value of theta does this equal 0? If I make this into a double angle formula and I make this into a double angle formula, then I'm going to have theta and 2 theta in the same statement at the same time. Trying to set that equal to 0 and solve would be extremely difficult. I can't have a function of theta, a function of 2 theta, and try to do the algebra. I really need one angle. So it'd be better if I left it like this and just factored. Now you notice I can clearly factor a cosine out of the top, but the bottom I can't. What if I change that to sine squared? So what if I change my cos squared to 1 minus sine squared? If I do that, then the top is cos theta minus 2 sine theta cos theta. But then the bottom would be negative sine theta, and this would be plus 2 sine squared theta minus 1. And my numerator and denominator right now are both factorable. Very, very nice. So my numerator, if I factor out the cos theta, would leave me with 1 minus 2 sine theta. And the denominator is a little trickier. If I wrote the following, let's replace sine theta with x. Let's be lazy. When you're looking at a quadratic where your variable sine theta, that's confusing. Just call sine theta x for a moment. Then wouldn't this be 2x squared minus x minus 1? But that's easy. Right? That was an easy factorization. So my denominator factors as 2 sine theta plus 1 times sine theta minus 1. Nothing's going to cancel here. And I'd like to know where this equals 0. When will this equal 0? Well, it's going to equal 0 when cos theta equals 0, or when 1 minus 2 sine theta equals 0. Now, to make it easier on ourselves, we could do every angle. We could do the plus k 2 pi. But since when I drew the picture, I only went from 0 to 2 pi. To make our life easier, let's just give the angles between 0 and 2 pi. Right? If my angle is 0, I can say 0, 2 pi, 4 pi, negative 8 pi, every multiple of k 2 pi, or just say 0. When is the cosine of theta equal to 0 on the unit circle? And you'd say theta is pi over 2 and 3 pi over 2. When is sine theta equal to 1/2? That's what that statement says there. That will be when theta is pi over 6 or 5 pi over 6. Okay. Hopefully you're all with me. I got 4 places where something really cool is going to happen. So let me go back to my picture. I'll erase this because I want to leave everything else here. I need that. So my picture, I almost got it. Oh man, sorry. I'm trying to make this actually look like what it's supposed to look like. All right, that's close enough. All right. Let me start with these guys. Pi over 6, 5 pi over 6. So that would be that horizontal tangent and that horizontal tangent. That's pretty obvious. 3 pi over 2. That's right there. So I've covered that one, and that one. But pi over 2 presents kind of a problem, doesn't it? Because pi over 2 is this guy right here. And I obviously don't have a horizontal tangent there. In fact, there's something, what does it appear? Think Calc 1 for a moment. What does that point appear to you? Because remember Calc 1 graphs. There's a word.
Cusp or
Cusp.
the other one?
No, a cusp. It appears to be because it comes to a point. It appears to be a cusp. But why did I get the derivative as 0 there? Oh, by the way, when theta is pi over 2, my numerator is clearly 0. But when theta is pi over 2, tell me about my denominator. It's also 0. So numerator and denominator were both 0 at pi over 2. So I don't have a horizontal tangent at pi over 2. If anything, you almost think of it like a removable discontinuity, except it's not removable. But in my derivative, if I put a pi over 2 in here, I get a 0 there, but I get a 0 here. So pi over 2 is probably the coolest place on this whole graph. It's where both numerator and denominator appeared to be 0. So that explains why it showed up here, because it also would show up down here. So this is just an exercise. So what I want you to be able to do is a couple of things. If I give you a graph in polar and it works nicely, can you convert it to rectangular? If I give you a graph in rectangular coordinates, can you convert it to polar? That's actually usually pretty easy, right? Replace X with our cos, replace Y with our sine, replace X squared plus Y squared with R squared, and then manipulate. Now, if I give you something in polar, can you tell me the derivative? Okay. If you can do that, can you tell me when's the derivative 0? Can you evaluate the derivative at any particular value? Because if you can, then you've kind of got the whole point. Okay, so that's the start of the calculus of polar coordinates. We have one lecture left on Wednesday, in which case we're going to do the integration. I'm going to find the area of this shape. Now, it looks terrifying if I'm thinking about it in XY coordinates. But if I do it in polar, it turns out it's not very difficult at all. If it's convenient to change something to polar, then working in polar is always going to be easier than working in rectangular. Next semester in Calc 3, you're going to find one of your greatest assets is being able to recognize when to change something to polar and then manipulate it in polar. And it almost always makes the problem significantly easier, not harder, much, much easier. X squares plus Y squares to different powers and things like that. All right, so this is a good stopping point.